Let's reconvene and take a look at the solution for exercise 3. So we'll start off by looking at erase. We're given a key, and what we want to do is we want to remove the key value pair from the local map over at the owner of that key. So we do an RPC to the owner of the key using getTargetRank to compute what the owner is. Then our remote function that gets executed is this lambda over here. It takes a distributed map as the first argument and the actual key value as the second argument. And all it does is invoke the erase on the local representative of the distributed object over on the remote side. And I'll remind you here that here we have a dereference, which gives us the local representative, and then we have an invocation of the erase member function on that resulting map. The other arguments for RPC are the arguments that the callback actually needs. So we have our local map over on the caller side. What happens is this gets translated to the universal name. The universal name gets sent over, and then it gets translated back on the remote end to the local representative of the distributed object over there. And then finally, we also pass the key as an argument here as well. This remote function doesn't return any value, so we just get back an empty feature as a result from RPC, and in this case, we return that directly as the return value of erase. So update does something similar. Here we have a key and we have a new value that we want to associate with that key. So again, what we're going to do is send an RPC over to the owner of that particular key. We use a lambda function a second time over here, but this time we have the distributed object and both the key and the value as arguments here. The lambda function just invokes the local update function, which abstracts away all the details of updating the value in the actual local map over on the remote. And again, we dereference our distributed object to obtain the actual map object over on the remote side. Once again, we pass the distributed object as the argument to RPC and our key and value. And again, that distributed object gets converted to its universal name. That gets transferred over, and then on the remote end, it gets reconstituted as the distributed object on the remote side. Okay, so this is an illustration of moving over computation to where the data is located. So again, we want to actually do an erase or an update. And so we just send the function that does that and all the necessary arguments over to the owner of the data to perform the operation. Okay, so moving onward, we can actually take a look at how a distributed hash table performs in UP++. Now, the example that we did was a simplified version. Our experiment here is actually using a somewhat more complex version that combines both RPC and RMA. Essentially, what it does is it does an RPC to construct a landing zone over at the owner, and then does an RMA to actually move the data over. The RPC itself allocates a landing zone and inserts into the local map at the target the combination of the key and a pointer to the landing zone, and then the initiator follows that up with an RMA to the target memory location. So without RPC, the sort of complex update would require explicit synchronization and two-sided coordination to accomplish. The resulting implementation scales quite well. The full details are actually in our IPDPS 2019 paper. But we see that the throughput increases relatively linearly as the number of processes increases. Moving forward, what we'll talk about for the rest of this portion of the tutorial is some more advanced UP++ features, as well as some details about how some of the things work under the hood. So we've already talked about remote procedure call. A reminder, the high-level overview is that the initiator injects the RPC, and a reference to the function as well as the argument values get packaged up together and sent over to the remote side. Then that gets in-queued on the target process, and at some later point the target process executes the function and notifies the initiator that the function has been executed. Any return values from that function are packaged up as part of that notification. Now, I mentioned at some later point. What determines that later point is something we refer to as progress. So our progress model is what ensures that the RPC eventually gets executed at the target and the initiator eventually gets notification of that. So when it comes to our model, UPC++ does not spawn hidden threads to advance its internal state or track asynchronous communication. The reason for that is that we want to keep the implementation simple and fast. If we introduce hidden threads, then we have to introduce synchronization as well for all of the internal data structures. The other thing that we get out of it is as an important feature of the programming model, which is that RPCs that are targeting any particular process, their execution doesn't actually mix. They get executed in serial at the target process, one after the other. And so that means that the RPCs themselves don't actually need to do explicit synchronization in many cases. And in fact, looking back at our distributed hash table example, we didn't do synchronization in insert or erase or update. And that's because we were ensured that while, say, an erase was happening, it wasn't possible for an insert or an update to be happening on the same process. So rather than having hidden threads to ensure progress, UPC++ relies on the application to make sure that progress happens. And so we actually provide a progress function that the user can invoke directly, but as we'll talk about in a moment, many applications don't actually need to do so directly. Before we do that, though, I want to mention that there's two different levels of progress. There's internal progress, which advances UPC++ internal state, including things like ensuring that asynchronous operations that have already been initiated, like one-sided operations that have already been initiated, make progress sort of at the network layer. But this internal progress doesn't involve any notification to the user. So it doesn't actually execute callbacks. It doesn't ready features. That's encompassed by user progress. So things that are directly visible to the application, those happen in user progress. And that includes things like executing inbound RPCs. So as I mentioned, we do provide a progress function for explicitly invoking either internal or user level progress. But many applications don't actually need to invoke progress directly because anything that blocks will invoke progress. That includes waiting on a feature. It includes a blocking collective operation like a barrier. If, on the other hand, a program has some long-running computation and expects local callbacks or remotely invoked RPCs to get executed during that time, then the application needs to explicitly call progress to make sure that happens. The fact that this is explicit means that the application can decide how much time to devote to running those callbacks using progress and how much time to devote to computation. So the user can tune their code to perform the right balance between progress and computation to provide best performance. When the application invokes progress, some number of outstanding callbacks get executed, but that some number can be zero as well. So the application needs to periodically invoke it when it's expecting callbacks. Within a callback, you can't actually directly wait on communication because, as we mentioned, anything that's visible to the application is something that happens in progress. And if a callback is already being executed, it's not UPC++ won't invoke a different callback at the same time. So a callback itself can't wait on communication, but it can actually chain things on the result of asynchronous operations. So it's perfectly legal to, for instance, chain a new callback on an existing feature, or to initiate new asynchronous operations within a callback. Since RPCs are executed serially, they provide a mechanism for ensuring atomicity. However, UPC++ also has remote atomic operations that can take advantage of offload capability of modern network hardware. The fundamental abstraction for remote atomic operations is something called an atomic domain. So the user creates an atomic domain with a particular data type, and currently we support 32 and 64-bit signed and unsigned integers. And then also a set of atomic operations. So in this case here, we have load, min, and fetch add. So this set encompasses the set of operations that the user intends to do on objects that are associated with this domain. And then what the library does is it takes a look at this set and then checks to see, is every operation in this set supported on the network hardware? If so, it will use offload. If that's not the case, then the library will use the CPU instead. So that way the library ensures that for any set of operations, it's using the hardware capability that provides the best performance and that provides the entire set of operations. Once we have an atomic domain, we can use it to do operations on global pointers. As an example down here, we've allocated an object in the shared segment using our new underscore operation. And then we do a fetch add on that pointer with the increment that we want and also the memory order that we require. Now this is an asynchronous operation, even though it's atomic. It is an asynchronous operation, so this initiates it and we get back a future that encompasses the result. In this case, this is a fetch operation, so we get back the old value. If we wait on the future, then that actually gives us the value itself, which in this case, if no other process has modified it, in the meantime, it will be 0. Another UP C++ feature is something called serialization. So when we do an RPC or when we transfer data from a source to a destination, that requires conversion of the object into some underlying data byte representation, and then reconstituting the object on the remote end. For C-compatible types, this is just a byte copy. So this includes things like primitive types as well as structs that are composed of primitive types. For more complex types, we actually provide an interface for specifying how that serialization should happen. For common STL types, we actually provide serialization built in, so things like vector, string, list, as well as nestings of these. And we also provide a mechanism for users to specify how serialization should work on their own containers. And the user has a choice of either doing a byte transfer or specifying that a certain set of fields should be transferred, or specifying that a certain set of values should be transferred and a constructor invoked on the remote end, or even full-fledged custom serialization and deserialization routines. For a container, serialization means that the elements get converted to their byte representations, transferred over to the remote end, and that data ends up in a memory buffer. Then the container itself needs to be reconstituted on the other side. So that means that the data needs to be moved out of the network buffer into private memory. So there is a hidden cost here in terms of deserialization, copying the data out of the network buffer. We have an alternative, something called a view, that actually elides that last copy if it so happens that an RPC is going to consume all the data before returning. So in this case, rather than giving RPC a standard library container, if we give it a view instead, we can do that by just constructing a view over the container. You can also construct a view over 2 iterators as well. When you pass this view to RPC, it does actually convert all the elements to their byte representations. But then on the receiver side, the data sit inside a network buffer. And so you get back a view over the network buffer inside the RPC callback itself. And then you can iterate over the network buffer itself. If the elements are actually C-compatible types, they actually do live entirely in the network buffer, and when you iterate over them, it's iterating over the network buffer itself. If, on the other hand, the elements themselves need more complex deserialization, then you can still iterate over them while the byte representations live in the network buffer, but each time you actually access an element, it performs a deserialization on the fly to actually give you the reconstituted object. But again, in both cases, we avoid the copy from the network buffer out into private memory. So in general, if we're going to be consuming the data directly within the RPC, a view provides better performance with fewer copies. On the other hand, if we need the data to live on past the end of the RPC, the most user-friendly way to do that is to just pass the container directly as the argument of an RPC, as opposed to making a view. One of the things that we alluded to previously is that UP C++ allows processes that share memory to actually get direct load store access to memory in each other's shared segments. Modern supercomputers have a hierarchical structure where we have cores arranged into sockets, sockets arranged into NUMA domains, perhaps multiple NUMA domains within a single node, and so on. And so some processes are actually closer together than others, and some processes can actually directly access memory that's located on other processes. So rather than a flat two-level hierarchy of traditional PGAS, where either memory is owned by the current process or it's owned by some other process, we actually have an intermediate level. We have the level of processes that share physical memory with another process. And our abstraction for that in UP C++ is called local team. If you actually invoke the local team function, you get back a team, a subset of the processes that share memory. So if we look at this example down here, we have two processes that are sitting in this shared memory domain, and another two processes that are sitting in this shared memory domain. So if we call local team on either process 0 or process 1, we get a team consisting of process 0 and process 1. And similarly, if we invoke local team on either process 2 or 3, we get a team that represents both of those processes together. To access an object that lives in the shared segment on another process in the same team, what we actually need to do is we need to obtain a global pointer to that object, and then we're allowed to downcast it. We covered downcasting of global pointers before, and we mentioned that the requirement for the validity of that is that you have to have direct load store access to that object. And that is the case for the processes that are within the same local team. So let's take a look at an example of doing that. So looking at the diagram at the bottom, the data structure that we want to set up is that we have a single array on each local team with multiple elements for each process. So rather than having the data split up between the individual shared segments of each of the processes, we'll have a single representative from each team store all the data for that team. So the first thing that we need to do is obtain the rank numbers and the rank count for our local team. In this case over here, we have two processes in each of the two local teams. And then process 0 has rank 0 in its local team, process 1 has rank 1 in its local team, process 2 has rank 0 in its local team, and process 3 has rank 1. Then we'll have only process 0 with respect to a local team do the data allocation. And the number of elements it allocates corresponds to how many processes are in that team. And the result of our allocation, because we're using a UP C++ function to allocate within the shared segment, is a global pointer. And then what process 0 in each team can do is it can broadcast that pointer to all the other members of the team. So here we're actually passing the local team as an argument to broadcast, which means this collective will be only over the processes within that team. So this is an asynchronous operation that results in a future. Upon waiting on it, we actually get the data encapsulated by that feature, which is the global pointer, and then we can store that in GP data for everyone on this local team. Once we have that, we can do a downcast to a local pointer, and again, this is legal because we know that this object lives on a process in the local team, and so therefore we have direct load store access to it. And then each process can go ahead and access it directly using standard C++ syntax for accessing an object through a pointer. So rather than, if we have some data structure that every process needs direct load store access to, rather than having a copy per process, we can actually just have one copy per shared memory domain. And so for instance, if we're looking at something like Xeon Phi, where we might have 272 processes within a single node, rather than having 272 copies on each process, we can just have a single one. And each of the processes have direct load store access to that. The other thing that we get out of this shared memory bypass is that we avoid going over the network layer to access data that lives on another process in the same team. And instead, what we can do is we can obtain a global pointer to it, cast it down to a raw C++ pointer, and then access it directly. This way we avoid the communication overhead, but we also avoid making a data copy as well. If we were to actually access it through the network layer, we would need to do something like an RGET or an RPC to get a copy of the data and then work on the copy of the data and then potentially make another copy in the other direction to update the value of that object. So far, we've relied on features and callbacks to get notification of the completion of an asynchronous operation. UPC++ actually has several different mechanisms for obtaining that notification, and features just happens to be the default one for most operations. Another thing that UPC++ provides is notification of intermediate completion steps as well. So for instance, if we do an output of some source data over to some target destination, there's some point at time at which the data has been injected into the network and we can reuse our source buffer. So we refer to that as source completion. Operation completion refers to the entire transfer having been completed, and that's the default notification. More specifically, the default completion notification for most operations is a feature that notifies us when the entire operation has been completed. So operation CX means we're looking at the operation notification event, and as feature means that we want the result as a feature. So that's just the default. We can actually specify other completion arguments to get another event or to get another mechanism, such as we'll see in a moment, promises or even RPC callbacks. So let's take a look at promises to begin with. For those of you who are familiar with C++ features and promises, a feature is the consumer end of the operation. So it's what receives the notification that the event has happened and that the values are ready. The promise is the producer end, so it's where the values get supplied and where the readiness is set. For a UPC++ operation that gives us back a feature, it actually creates an implicit promise internal to the library. So what we get back is the future side of that asynchronous operation. However, we can actually create our own promises as well, and then use it, and then pass it to a UPC++ operation to use as the producer end. And in fact, this allows us to construct a single promise and use it with multiple communication operations. So as an example, we've done that over here. We have a promise here, which we're just using to keep count of the number of operations, so we don't actually have any data values represented here. So that's why the template argument list is empty. And then we launch a number of arget operations providing the same promise object. Now, we do need to wrap this promise into a completion object so that it meets the right interface for arget. So in particular, here we're asking for the operation completion event, and we are asking for that to be provided as a notification on a promise. Once we've initiated all of these arget operations on the promise, we can close registration of the promise, which gives us back the future end, the future corresponding to that promise. And again, here we just have the notification being encapsulated in the future, so we don't have any values here. If we call wait on the resulting future, it waits for all the outstanding operations that have been associated with this promise to complete before returning back to us. So this gives us the ability to wait on a large number of operations using just a single promise, as opposed to what we saw before where we constructed a DAG of operations. Another interesting case of non-default completion is to enqueue a callback over at the remote end. So this is particularly useful for something like output, where we're doing a one-sided copy of data over to some potentially remote destination, and we want to notify the target that the data have arrived. And so the way that we can do that is there is a remote completion event that gets triggered when the data have arrived. We can provide an RPC callback to be run when that happens. And so here we've actually provided some computation function to consume the data that have been transferred. So what we're doing here is we're doing an RMA put that informs the target upon arrival. So we actually refer to this as a signaling put. The implementation in many cases can actually transfer both the underlying data for the one-sided communication as well as the RPC data within a single network level operation. And what we get out of this is that we have a coupling of the data transfer with a synchronization. And so we get something that gives us an abstraction like message passing, but without many of the overheads. In particular, all the metadata is provided by the initiator, and the receiver doesn't need to know anything. The only thing that the receiver needs is to be attentive, meaning that they are invoking progress either implicitly or explicitly, so that this callback eventually runs at the destination. So you can imagine taking our Jacobi example and moving the edge computation into an as RPC callback as opposed to doing a wait and then doing it locally. Another feature that UPC++ provides is the ability to copy between device and host memory, and in fact any combination of local or remote host or device. So this is for machines that have, for instance, GPUs or other accelerators. Currently we support CUDA devices, and so what we have is we have a version of a global pointer that's actually parameterized by the device kind, and in this case it's a CUDA global pointer. And so this references memory that actually lives on a device as opposed to on host memory. Then what we can do is we can pass global pointers representing any combination of local or remote host or device memory to initiate an asynchronous copy operation between those locations. And of course, this is asynchronous as all of our other communication operations, so we get a future back which we can then wait on. One final feature I want to talk about is non-contiguous RMA. So we looked at just a contiguous case where you have a source pointer and a destination pointer and a count of elements, and it does a contiguous transfer from the source to the destination memory. So this is sufficient for the 1D Jacobi example that we saw. However, if you're doing Jacobi in higher dimensions, then the ghost data is actually strided, as opposed to just being a one-dimensional contiguous piece of data. You could implement this with just standard rput or rget, using a loop and fine-grained access, but it can be much more efficient to pack the data and aggregate the communication. We actually have a facility in UPC++ to do this automatically. So we have several different versions of non-contiguous RMA that, underneath the hood, try to pack it and pipeline the data transfer as efficiently as possible. So we provide 3 different APIs. The first is an IOVEC style set of iterators over pointers plus length. So this provides the most generality, but it pays the highest metadata cost. We have regular, which is iterators over pointers with a fixed length. And then finally, we have strided for something like a Jacobi go-cell exchange, where we have some subset of a dense multidimensional array. So again, we're trading off generality for the amount of metadata and the amount of overhead required to do the packing and unpacking operation. Once we make a choice of which of these 3 interfaces to use, we're relying on the UPC++ library to figure out the best way to do the transfer. So that's all I have as far as feature overview. We didn't get to every single last feature in UPC++, so I'm going to point you to some additional resources. You can get to everything from upcxx.lbl.gov, and that includes things like resources from this tutorial as well as other tutorials. We have a written UPC++ programmer's guide to give high-level advice and feature overview. We also have a formal UPC++ specification that includes all the features that we talked about, plus the ones that we didn't get to. Links to various publications, optional extensions that people have written for UPC++, as well as contact information and our support forum. We will end the feature overview over here, and I will leave you with some quotes from some of our users about how useful UPC++ has been to them. We'll take a short break with another opportunity for live Q&A, and then after that we'll look at a couple of application case studies of using UPC++ in larger applications.